In this video here, we're going to take a look at Floyd's algorithm. So we can use Floyd's algorithm to find the shortest path between every pair of vertices in a network. And Floyd's algorithm produces two tables. Now the first table shows the minimum distance between each pair of vertices, and the second table can be used to find the corresponding root. And unlike Dijkstra's algorithm, Floyd's algorithm will tell you the shortest distance between any pair of vertices in the network. So before we work through a practice question together, as always, let's formally define Floyd's algorithm. So the main question for this video here is, how does Floyd's algorithm actually work? So to do this here, we're just going to follow 7 steps. So for step 1 then, what we do here is we complete an initial distance table for the network. Now, if there's no direct route from one vertex to another, what we do then is we label the distance with the infinity symbol. For step 2, we then complete an initial root table by making every entry in the first column the same as the label at the top of the first column. We then make every entry in the second column the same as the label at the top of the second column, and so on. You can see where that's going, right? Now for step 3, in the first iteration, we then copy the first row and the first column values of the distance table into a new table. And from there, what we then do is we lightly shade these values. Now for step 4, we then consider each unshaded position in turn, comparing the value in this position in the previous table with the sum of the corresponding shaded values. Now there's 2 points to note here. So note then, that if x plus y is greater than or equal to z, then we copy z into the new table. In other words, there's no change, right? And the aim here is to keep the smallest possible values in the table. Now for the second point, if x plus y is strictly less than z, then we copy x plus y into the new table, and we write a in the corresponding position in the root table. And once all the values in the unshaded area have been considered, the first iteration is complete. Now, just in case you're wondering here, x, y, and z are just 3 arbitrary random values that I've kind of plucked out of thin air, basically. If you just kind of draw this here, I'll quickly do it at the top, right? So let's just say that we've got A, B, C, and D here. I'm kind of just squashing this on. It's not going to be pretty. I've also got A, B, C, and D. Then what I get here is something like this. So obviously for the first iteration then, what I would do here is highlight. So I'll do it here. So I would highlight then. I don't know if it'll actually do it here. That's not too bad. And I would highlight down this column here, like so. Okay. Now, what I'm looking for then, oops, I don't want to highlight here. Let me just change that. Sorry. Back to my pen. So let's just say then that this value here is x, this value here is y, and then this value here underneath is z. Then what I'm looking at here, and again, I'll just highlight this. So going back to my highlighter, and let's just do this in, we'll do it in blue here, just kind of make it a bit more distinct. What I'm looking at then is y here. I'm looking at x, and we compare that to z here. Okay, so as we just mentioned then, if x plus y is greater than or equal to z, then we copy z into the new table. And if x plus y is strictly less than z, then we copy x plus y into the new table. We would write a in the corresponding position in the root table. So for the root table here, oops, going back to my pen again. I keep forgetting to go back to my pen. There we go. What would that look like? So again, I can just squish it on at the top here. I appreciate that this isn't the neatest, but you can hopefully follow along here. So on the top, we've got A, B, C, D, like so. Going down there, I've also got A, B, C, D. That's not the neatest, but it doesn't matter too much, right? I'm going to kind of erase it in a moment anyway. So I'd have A, B, C, D. Now along the second row here, again, I get A, B, but where the C is here, okay, what we're doing here is replacing that with A, right? If x plus y is strictly less than z. So what I do here is replace that with A, because we've gone via A, right? And we put that inside square brackets like so. Okay. So just to make this look a little bit neater here, I'm just going to quickly clear that. But if you want to kind of make a quick copy of that, right, just pause the video here and just quickly jot down these 2 sketches. Okay. So let me just quickly clear the screen here. like so. And let's just continue then. Now for step 5 then, this concerns here the second iteration. So for the second iteration then, what we do here is we copy the second row and the second column from the last iteration into a new distance table. And again, all we do here is we lightly shade these values. Now for step 6 then, at this point here, we just now repeat step 4 with the new unshaded positions. And this time, any changes will result in a detour through B. And so you should write B in the new root table, in each case in the position corresponding to the changed value. And then finally, for the very last step here, step 7, just note then that if there are n vertices, then completing the algorithm will require n iterations continuing in the same way. Okay? Now, my opinion here is explaining Floyd's algorithm in this way, in 7 steps. Intuitively, doesn't make too much sense. Maybe that's just me. But really, I think the best way to demonstrate Floyd's algorithm here is just run through a quick practice question. Okay? So that concludes this introduction here to Floyd's algorithm. To finish with then, let's just run through a quick practice question together. So let's just get started then with this practice question here. Now for this question then, as we can see here, right, we have this network. And this network here shows the direct roads between 5 villages. So that's A, B, C, D, and E. And as we just mentioned, right, they're represented by the network below. Now the weight on each arc is the time in minutes required to travel along the corresponding road. And Floyd's algorithm is to be used to find the complete network of shortest times between the 5 villages. So for the first part of this question, then that is part A, right? It just says based on the network above, complete the initial time matrix. Now in your exam, you'll be given the outline of the initial time matrix, right? All we need to do then is just complete, and hopefully it should be nice and straightforward. So looking at the network here then, what do we get for the initial time matrix? So for example then, going from A to B here, that would have a weight of 10, right? What we're looking at here is the direct routes for the initial time matrix. So from A to B, that has a weight of 10. Where's the units here? So it's minutes, right? So 10 minutes then. So we input 10 into the initial time matrix. Now for this network here, as we can see, so we can't loop from A to A, B to B, C to C, so on and so on. So along the leading diagonal here, they just insert dashes, right? And as I just mentioned then, that just shows that we don't loop from A to A, B to B, C to C, so on and so on. What's also important here is for this network that we're given, we don't have any directed edges or directed arcs here, and that's important. Now, why is that important? Well, what that means then is for the initial time matrix here, it will actually be symmetric about the leading diagonal. So if this value here is 10, that means that this value here is also 10 because it's symmetrical about the leading diagonal. Okay, so let's just keep going then. What about A to C here? So from A to C, as we can see then, that has a weight of 15. So we just simply insert 15 into the initial time matrix. And again, this value here is also 15 by symmetry, right? Let's just keep going then. So what about A to D here? So going directly from A to D, well, there's no way that we can do that, right? It's impossible. So the way that we denote this here then in the initial time matrix is by using the infinity symbol. The infinity symbol there, like so. And same again here for this value by symmetry. And then finally, the last value here along the first row, A to E then, what would that be? So nice and straightforward then. That's simply 5. And again, this will also be 5. Perfect. Let's just keep going. So what about B to C then? So from B to C here, that's simply 3. And same again here for this value by symmetry. B to D, so that is 8 here. So input 8 into the initial time matrix, and same again here. And then finally, B to E here. So B to E, that has a weight of 4. So input 4, and same again here. Perfect. Okay. We're not too far off now, so let's just keep going then. So what about C to D here? So from C to D, nice and easy, right? That's just simply 2. Same again here. That's also 2. What about C to E then? So from C here to E, so going directly here, we can't do that, right? It's impossible. So again, the way that we denote this here is by using the infinity symbol. Okay, like so. And then for the final value here, because obviously these two values will be identical by symmetry. So from D to E then, so from D to E here, that just has a weight of 7. Perfect. So this here then, this is for part A, right? What this gives us here then is a solution to the initial time matrix. And now for the final part of this question then, that is part B, what we're told here is the time matrix after 4 iterations of Floyd's algorithm is shown below. So that's this matrix here, right? Now for part B then, all we want to do here is just perform the final iteration of Floyd's algorithm that follows from this time matrix above. And we must also show the time matrix for the final iteration. So again, in your exam, you'll be given the outline to the final time matrix. And all we need to do here then is just complete it, right? So where do we begin here? Well, let me just begin then by denoting here that this is for part B, right? Always a good step. What I'm also going to do here is just grab a highlighter. So what I'm concerned about here is this row, so row E, and also this column here, column E, right? And that's because this is the final iteration. If it was the first iteration, it would be this row, this column, second iteration, this row, this column, third iteration, this row, this column, but you get the idea, okay? Now, what we want to do here is just consider then whether we can shorten the distances, for example, of AB, AC, AD, so on and so on, by going via E. Now, there's two ways that we can do this here. We can use the method that we mentioned in the introduction by using the given time matrix here, or what we can also do then is use the given network here, right? Now, either of these methods is absolutely fine. I personally prefer using inspection and the given network here to kind of deduce whether it would be shorter, but if you want to use the matrix method, again, that's absolutely fine. But no matter what, we should clearly get the same answer. If we don't, something's gone horribly wrong. So let's just make sure then that we do get the same answer here. So I'll start with the visual approach here and then kind of walk through the matrix method as well. I won't go into a massive amount of detail for the matrix method. I'll just show a couple. You should hopefully get the idea. Okay. So using the given network here then, what I need to consider here is can we shorten the distance then for AB, which has a weight of 10 based on this fourth iteration, by going via E. So what I need to do here for A to B is go from A to E and then E to B, right? So that is A, E, B. Now AEB has a weight of 5 plus 4. So 5 plus 4 is 9. And is this value here, which is 9, less than this value here? Well, clearly 9 is less than 10. So 9 is less than 10. And in that case, then, we would now replace this value here in the final iteration, right? So therefore, replace. Now, before I insert that value then into my final time matrix here, just 2 quick points then. So the highlighted column, the highlighted rows, they won't change. So I can quickly just drop those into the final time matrix. So 5, 4, 7, 7. Same again here for this row, right? So 5, 4, 7, and 7. Perfect. And that nicely leads me on then to my second point here. And it's pretty much identical to, so the matrix won't be identical to this matrix clearly. But what I mean here is this matrix here will also be symmetrical about the leading diagonal. So as indicated by this column here and this row here, as they're symmetric about the leading diagonal. So that should save us quite a bit of time here as we complete the final time matrix. Let's just keep going then. So what about A to C here? So A to C here, what would that be then? So for A to C here, I'm going to go from A to E, then from E to B, and then B to C, right? So A, E, B, C. So what's the weight of this here then? So that's 5 plus 4 plus 3. So that's just 9 plus 3, which gives us 12. Now, is 12 less than this value here? So clearly 12 is less than 13. So 12 is less than 13. And again, because it's less than this value here, we replace it. So I forgot to do it for this value here, but don't forget to actually drop it into the final time matrix, right? So A to B then, this is 9. Now, once you find a shorter value, don't forget that we need to put this inside square brackets. So 9 goes inside square brackets. And the same is true here for A to C, right? Because 12 is less than 13. So 12 goes inside square brackets like so. And again, via symmetry here, this will be 9. Oops. And this will be 12. Perfect. Good stuff. Let's just keep going then. So once I've done this value here of AD, I'll show you how this would work with the time matrix here, right? So for AD then, this is A to D. What route would I take here? So I'm going to go from A to E because we need to go via E, right? So A to E, and then we can go from E to D. So 5 plus 7 is 12. So A, E, D. So AED has a weight of 12, and 12 is less than 15, right? So therefore then, again, we replace here. So we replace it again in the final time matrix. So 12 less than 15. So we put 12 inside square brackets. So that's the first row and the first column complete. How would that then work with this time matrix here? So this would be the method that we mentioned in the introduction. So to do this here, what I'll do then is grab my highlighter. I'm going to change the colors up a little bit here. So I'll use light blue then. So what we're looking at here is AB to begin with. So what I need to do here is go from A to B, but we need to go via E. So to go via E then, I'll do this in a different color as well. Let's do it in light green here. I go from A to E. So that's got a weight of 5 here. And then we go from E to B, right? Which has a weight of 4. So 5 plus 4 is 9, exactly as we got here, right? They shouldn't be different. So you should get the exact same value as we've got here. Perfect. That's always positive, right? If we didn't get the same, I would be worried. And again, all we do here is we compare that. I can't speak. We compare that to the blue value here, which is 10. Now, clearly 9 is less than 10. So again, we just replace it. Nice and easy, right? What about A to C then? So again, I'll do this in a different color. Let's use a light blue here. So we're looking at 13 here, okay? And again, let me use a different color here. Purple's a little bit dark. I'll try orange. Let's see how orange comes up. I can't speak anymore. Too many videos recorded in one day, but we're nearly there now, guys. Let's keep going. So again, we go via E here. So A to E, which has a weight of 5. And then we go from E to C, which has a weight of 7. So again, 5 plus 7 is 12. We get the exact same value. Perfect. Good stuff. And again, 12 is less than this value here in blue. So again, we just replace it, right? As we can see here then on our final time matrix. So for the final one here then along this row, this is AD. So we highlight AD then. So that has a weight of 15. And again, we need to go via E here. So I'll use light green again. In fact, actually I won't because I've used it already. I'll do it in red here. So we go from A to E. So we go via E. And then we go from E to D, right? So 5 plus 7 is 12 again. We get the exact same value. If we don't, something's gone horribly wrong. And is 12 less than this value here? Well, clearly 12 is less than 15. So again, we replace it exactly as we've got here, right? Perfect. So that's how the matrix method works. I won't go through each individual value here. I've just done the first row and the first column, but hopefully that demonstration there helps explain how we actually use the matrix method to implement Floyd's algorithm. Okay. Now, for the remaining values here, so that is BC, BD, and DB and DC, these values won't actually change here. Okay. Did I miss CD as well? I think I missed CD, but you get the idea. These remaining values here, right? These values here won't actually change. There's no way to reduce the distance, for example, of BC. You can use the matrix method to quickly verify this, right? So BC then has a weight of 3, but I need to go via E. So B to E has a weight of 4. So no matter what, 4 is already bigger than 3. So clearly, we're never going to be able to reduce that. So BC then, we just keep 3 here. And for BD, let's quickly verify that here then. So B to E has a weight of 4, but then E to D has a weight of 7. So 7 plus 4 is 11. It's clearly greater than 5. So again, we can't reduce that. So we input 5 there like so. And again, by symmetry, that's 3 and that's 5. Perfect. If he was using inspection here, we'd just be looking at the different paths here, right? So for example, then to get from B to C, so B to C here, we're going via E. Well, clearly if I go from B to E, that's got a weight of 4. B to C as a weight of 3. So we've already exceeded that, right? So again, we can't reduce that, as we quickly demonstrated before with the time matrix here. Again, we can't reduce it, so we just input the original value of 3. And then same again here for B to D, right? Just use the network here to quickly verify that. And same again here, as we mentioned before, right? We cannot reduce C to D, right? Again, you can quickly verify that using the time matrix here. So C to D, that's a weight of 2. We're going via E then, so C to E, that's got a weight of 7. So we've already exceeded it. So again, we can't reduce it. So that's 2. And again, by symmetry, that's also 2. Okay. And there we have it then. So as you can see, actually implementing Floyd's algorithm is pretty straightforward. And as I mentioned before, it's completely up to you which method you use here. If you want to use the matrix method, that's absolutely fine. And hopefully this quick demonstration here did help kind of illustrate how we actually use the time matrix to complete Floyd's algorithm. Or you can use a visual approach here, as I started off with, to complete the final time matrix as well. Either of these two methods here is absolutely fine. And as I mentioned before, you should clearly get the same answer no matter what. Okay. But there we have it then. So this here gives us the time matrix here for the final iteration of Floyd's algorithm. Okay. And there we have it then. So that gives us the solution here to the one practice question for this video. And that brings us to the end then of this video here on Floyd's algorithm.